So what I do is I develop Tau. I'm the principal investigator of the Tau Commander project. And I also use Tau to improve the performance of HPC codes and develop my own codes. So I have the pleasure of being both a Tau developer and a Tau user. I get to try it from both sides here. So today I'm going to spend most of my time talking about Tau, introducing you to it. I think a lot of you are at least heard of Tau. Notice this is Tau with a U, not Tau with an O. Tau with an O is a different thing. I'm going to tell you a bit about the Tau Commander project, and I'm going to show you some case studies of applications done here at Argonne that achieved significant performance improvement using Tau. So when I was just a kid, I learned how to do basic math on an abacus, which is actually a lot of fun. An abacus is a great tool for doing basic math. And it's so simple and intuitive that even a child can use this thing. The main problem with it, of course, is it's not really a high-performance machine. If you're a world-class abacus user, you can manage probably 8 flops on this device. So given the average human metabolism, that's about 10 watts per flop, which is not really great. So obviously, we use supercomputers to do math because why? They have better performance. They have better efficiency, a lot better performance, in fact. If we want to keep pushing this silly abacus thing, MIRA is equivalent to about 1.25 quadrillion abacuses. Or to put it another way, if you gave every human being on the planet 173,000 abacuses and had them operate them simultaneously, you'd get close to MIRA. So the performance of this device is obviously much better than the devices of the past. But the disadvantage, of course, is that it's much more complicated and it's harder to use. If you asked a child to use this, I think neither the machine nor the child would come back in the same condition. It's very difficult. So for the metrics we care about, performance, efficiency, productivity, we use supercomputers. That's why we're here. So if we're not getting these things, then we should just go back to using paper and pencil, right? So if your performance and your efficiency are low, you want to improve that. Now, I use the Tau performance system to improve performance and efficiency of my code. So Tau is an integrated toolkit, meaning it includes a lot of different utilities with a lot of different features and a lot of different capability. It has the ability to analyze the whole system, your application, all the way down to the hardware. And this is a must as we go to large scales. You know, if we're already at the petascale, if we're going to go to exascale and beyond, we're going to have to use a whole system approach to performance evaluation and improvement. And it's free. It's free, open source, BSD license. You can download it, use it in your own applications, your own toolkits, integrate it into your own application frameworks, whatever you want to do. Now, the other question is, Tau can improve your performance and your efficiency, but how are we going to improve our productivity? Randall Munroe suggests playing with a coefficient of friction on our desk chairs, but I would say we could use something called Tau Commander, which is a project I'm working on right now to improve the productivity of Tau users, basically making Tau more accessible to people who are not computer scientists or advanced, really intelligent, creative scientists like yourselves. All right, so I'm going to talk about Tau for a little while. Tau, like I said, it's available on all the Argonne systems, available at all the national labs, in fact. It's been developed for over 20 years. It's a comprehensive toolkit. It performs both profiling and tracing, either or a combination. It's very scalable, goes out to many hundreds of thousands of cores, no problem. And it provides instrumentation, measurement, analysis, and visualization of performance data. It also has a capability to mine data and to highlight bottlenecks and so forth in your code based on analysis of multiple profiles or traces. So the main things Tau does, as John said in his talk, he made a distinction between profiling and tracing. Profiling, again, is this aggregate of performance data. It contains no timeline information, so the files tend to be a little bit smaller. They show how much time was spent in each routine, or how many flops, or how many L2 cache misses, and so forth. Whereas tracing shows when events take place. And both types of data are very useful and very effective for finding performance problems. Now, within profiles, which is what I'm going to talk about most today, you have several different types of profiles. You have your flat profile, where all the data is simply aggregated. So if you have a call to foo, and it occurs multiple times in your program, you'll see one timer for foo aggregating all the calls to foo. A call path profile is, as we saw in the previous slides, it just involves a call path. So if for every call to foo, you'll have a different timer showing time spent in foo along that call path. And I'll be showing some slides showing pictures of the tools in Tau here, so you'll actually be able to see what these look like. And then finally, phase profiles. Your Typical scientific codes often have multiple phases: initialization, transport, chemistry, finalization, and so forth. And it's nice to be able to separate the impact of I/O in the initialization, for example, from I/O in your transport phase, if you're interested in, what is the time spent in checkpointing or something like this. So for each type of profile, you get a different amount of data. So then you need to decide, how much data do I need? Tau, by default, if you just ask for profiles, it'll give you flat profiles, which is usually a great start. But then you can move up this, I would say, very logarithmic scale, going from the order of about kilobytes up to about terabytes if you're using traces. And all levels of profiles and traces support multiple counters. So at every different type of profile, you can get hardware performance counter data, time data, and so forth. You're not restricted. You don't have to rerun your code every time you need a different kind of metric. The other distinction I need to make is that Tau supports both direct measurement via probes and indirect measurement via sampling, which is what HPC Toolkit uses. Tau supports both simultaneously or either or. The advantage to direct measurement by probes is you get exact measurement. As soon as an event occurs, you measure exactly where the event occurred and how and what was its impact. This also gives you very fine-grained control on what parts of your application are you interested in. So for very large applications, maybe imagine you have an application with a Python wrapper that calls Swig-generated C++ that calls Fortran. You might not care about most of this stuff. Maybe you just care about what's in the Fortran solver. And with direct instrumentation, you can instrument exactly that part of the code and ignore everything else. So this helps you control your overhead and also cleans up your profile a good bit. Sampling, of course, it's very low effort to get started with sampling. You simply plug in your binary codes and start sampling the program counter, and you get data back immediately. And it avoids blind spots. So if I don't have the source code for a third-party library, I can still get information from there using sampling. So that's a great advantage. Used in conjunction, you can get a very good view of what's actually happening inside your application. Now, you can instrument your code manually, meaning you go and rewrite your code and insert tau start, tau stop, and so forth. But if you have a lot of code, this becomes really burdensome. So we actually have parsers and compiler wrapper scripts that will automatically parse your source code and insert the hooks and the probes directly into your source code for you. Now, to use these, all you do is replace your makefile call, your compiler calls with the calls to Tau's compiler wrapper scripts. That's it, really. You don't have to do much more than this. And these scripts will go through several iterations of trying different parsers, trying different instrumentation approaches before they finally give up. So there's a good chance that one of the things that it tries will automatically produce an instrumented application for you. This is, I would say, 80–90% of the codes, this is all you have to do. Now, Tau supports a great many HPC platforms. I would say that it supports all HPC platforms by definition, meaning we work closely with vendors and researchers and everyone who's developing these systems, so that as soon as a new one is available, we port Tau to it. And this has been going on for 20 years. So we do support the Blue Jeans, we support the Intel Xeon Phi, we support CUDA, we will be supporting Knight's Landing when it comes out. Pretty much, we also support Android. Tau has been run on the cars, computers in cars. It's found in a lot of interesting places. I've run it on airborne real-time systems. So it can be very lightweight and can be very versatile. Tau's architecture and workflow. So the architecture closely matches the workflow. As a user, you go through 3 steps, basically instrumentation, measurement, and analysis. This produces the data that you need to improve your code. So instrumentation, this is just the process of adding probes to your code, either using our source code instrumentation via compiler wrapper scripts, or creating library wrappers. If you have a third-party library and you want to perform direct measurement on, say, HDF5 or BLAS or LIPEC or something like that, you can use Tau to generate a wrapper library where every call made to that third-party library first invokes Tau and then invokes the library, so that Tau collects the data per call. And then we also support rewriting binaries. So if your binary is sufficiently malleable, we can actually insert the hooks directly into the code after the fact. And this has been very useful for third-party applications or vendor applications where they don't want you to see the source code at all, or maybe defense applications. Once you have your instrumented code, you want to measure what's going on. You run your code. Simply running the code, once it has probes, will provide you direct measurement. You can enable sampling. Again, you get measurement this way. And it's at this point that you use features such as throttling. So throttling, tau watches its events, and if it sees there's a routine that's being called rapidly, and in a short period of time, it stops measuring that routine and just marks it as throttled. And this cuts down on overhead dramatically, because if there, say you have like a min-max function, you don't need to know the time spent in min-max. You just clean it out of the profile, and tau will do this automatically. It also interfaces with external packages such as PAPI. So this is where our hardware performance counter data comes from, is PAPI. We also have an interface to RAPL, so we can get power information and show that in the profile, which is very fun to see on a timeline. If you hit a compute-intensive part of your code, you'll see your power consumption jump. And then finally, you want to analyze this data. So now I've got my profiles, I've got my traces. What do I do with that? Well, Tau ships with several data analysis, data mining, and data visualization tools. And you get things like this. This is an example of a topology view of the blue gene showing a code executing. We can see this is time spent in routine by MPI rank. So we've artificially said, if your rank is this, run longer than if your rank is that. And it shows up very nicely in the topology view. These are the steps you would actually take on MIRA or Vesta or one of these ALCF systems to run Tau. Tau is installed here. Soft perf tools Tau is Tau latest. And now every Tau installation comes with several Tau makefiles. Makefile is a little bit of a misnomer. They're really more like configurations. The Tau makefile tells Tau what type of metrics to add to gather and what compiler flags to send to your application so that the correct metrics are generated. So here we have a Tau makefile. It's going to use BGQ, high resolution, high efficiency timers. We're going to use PAPI so we can get hardware performance data. We're going to gather MPI data, so time spent in collectives and so forth will be visible. And we're going to use PDT, source code parsers. Any makefile that shows PDT in the name, that's used for direct source code instrumentation. Doesn't mean you can't use sampling, but it means you will be able to use source code instrumentation. Once you know which Tau makefile you want to use, on the blue gene, just do soft add Tau latest. That'll put Tau right in your path. You immediately have access to the Tau compiler wrapper scripts. Set your Tau makefile as shown. Optionally, you can set this Tau options environment variable. You run the tau_compiler.sh-help to see what the available options are there. There's quite a few. And then finally, change your calls to the compilers to the compiler wrapper scripts to perform the automatic source code instrumentation. Execute your application as normal. If you used a makefile with PAPI, you can set the Tau metrics environment variable to specify PAPI metrics. For example, here I'm looking at L2 datacast mishes on the blue gene queue. This will generate a whole bunch of files in your folder. They'll be named profile.something something something, which identifies the exact rank of each thread in your application. There's also an option to have Tau merge these into a single file if you want to cut down on file I/O. So that you may also have a single file there if you specify that option. Either way, you analyze your performance data by using one of these tools, pprof, which will just dump the data to your console, or paraprof, which is what I'm going to spend most of my time showing you. All right. So now I'm going to show you several charts. These are actually coming from paraprof, Tau's profile visualizer. Paraprof is used to look at usually one profile at a time. You can open multiple profiles in paraprof, but the data you'll extract is on a per profile basis. So I'm looking at a profile of one profile, executing on 1K cores, and this is the SMPM application. I'm showing exclusive time, and my MPI all-to-all is clearly leading in terms of exclusive time. Right up there. This is the mean across all 1024 cores. If I want, I can look at each rank as well. Open paraprof and click on one of your labels, either the mean or the known. They don't look like buttons. They look like labels. So most people don't realize that you can actually click on them. But you can. I suggest you do. Next, if you want to look at floating point instructions, you can select a different metric from the metric option, from the metric menu. Here I'm showing floating point instructions, as I said, and immediately we see that our FFT routine is the most floating point intense region in the code, which is what you expect. MPI all-to-all is not visible here, which, again, yeah, you would expect this. If you saw a lot of flops in MPI all-to-all, you'd wonder what's going on. So that makes a lot of sense. Whereas if we look at our L1 data cache misses, we see now that our FFT routine is back at the top. So FFT might be a good place to look at optimizing, perhaps, to look at loop interchange or strip mining or something else, one of these types of cache optimizing approaches inside our FFT. MPI all-to-all is back up at the top, which is what you'd expect, again, from a routine that moves a lot of data around. It shouldn't be sitting in cache. Another thing Tau can show you is how much memory does your code use. Now, this is really useful information in a low memory environment like BlueJean, where I can see the high water mark of my application, total memory utilization for heap. You can also see the total amounts of bytes that were allocated and deallocated over the lifetime of your code. Now, if you have a call path profile, which is what I'm showing here, you have this tree structure showing, breaking out the allocation events per every node of the tree. Now, notice that a call path profile includes all the information of a flat profile as well. That is, I still have my aggregate events for free and malloc, but I also have those events per routine. So this helps you find which routines were allocating the most memory or deallocating memory and so forth. That can be useful in debugging. You can see what are the I/O characteristics of your code. Here I'm showing write bandwidth and bytes written per file. To get this again, just open the context event window. And I can also see MPI I/O. So here's the MPI I/O write bandwidth in peak write bandwidth, and you see these triangles here. I could expand the call path again and find the exact calls to MPI I/O and see on a per call basis who had the highest bandwidth, the most bytes written, and so forth. And then one thing that we all have to be concerned about on a distributed memory architecture is collectives. So we have special events specifically for how much time is spent in collectives and what were the size of the collective messages. So we have MPI bcast, reduce, and so forth. It's very easy to bring up both these windows side by side and see exactly who is slowing your code down or who is not scaling due to some sort of collective operation. Tau includes some really great 3D visualization features. These are more than just eye candy. They're actually very useful. So in the 3D visualization, we have on one axis, this is the threads of the application, and these are the routines in the application, or code regions. Now, it becomes immediately obvious if there are any kind of patterns in your data when viewed in this way. There's a clear inverse relationship between these two functions. And in real-world applications, you often see, for example, an inverse relationship between something like MPI send and MPI barrier. And this will show you immediately that somebody is stuck waiting in a barrier before they can send their data. And that might be a good opportunity to use something like MPI iSend to overlap your computation and communication. You can also visualize the communication matrix. So here I'm showing this is threads on both axes, and this is exclusive time. This will show you exactly how much time was spent sending from one node to another node. And this is a fun graph, too, especially in CFD applications. This often looks like the sparsity structure of your matrix, which is usually something you would want to see. You often see a lot of computation close to nearby neighbors, and then further neighbors are not communicating so much. That's a good thing. If your communication is showing lots of hotspots off the main diagonal, then that means nodes are having to talk to nodes far away from each other. And you might need to optimize that, depending, of course, on how MPI actually places your nodes physically. So how does it place your nodes physically? Well, we can look at the topology visualization. If you know that if you don't know how MPI is placing your nodes in the machine, you can load the topology for your machine and map your data onto that topology, which will immediately show, oh, hey, there's a hotspot, in rack 5. All my data has been stuffed up in rack 5, and everybody's trying to talk to the same switch or something like that. So all the previous charts are from ParaProf. ParaProf, as I said, deals with a single profile. But what if you want to mine data about scalability or parallel efficiency? Well, you can use PerfExplorer. PerfExplorer operates on multiple profiles simultaneously. It performs statistical analysis and visualization of multiple profiles to do things like this. You can ask, how does each routine in my application scale? So in this application, I'm running from about 1,000 cores to about 12,000 cores. And as the number of cores increases, time spent in MPI wait all begins to dominate. So this is a percentage, 0 to 100% of the application runtime. And wait all and write save file become serious problems at scale. It might be limiting our scalability. Now, since it is a percentage, how do you see the absolute time? Maybe this is not a problem. Maybe our time is dropping off significantly, so I don't care how much time is spent here. Well, you can look at a stacked bar chart view of the same data, which gives you the absolute value in time. So what we see here is that from about 4K cores to 65K cores, at 65K cores, I'm actually slower. And this has been due to the effect of routines inside the application. So now sometimes it's really obvious when you open these charts, who are the culprits in scalability. But what if it's not immediately obvious? So this was an application that wasn't scaling well, or it had, actually I should say, it scaled, but it performed very strangely for certain core counts, performance-wise. So you can you can correlate events with the application runtime in PerfExplorer. And this will give you a confidence factor showing a correlation between time spent, for example, in the transpose routine and the application runtime. And what we saw was that at these particular core counts, transpose performed very efficiently, and at other core counts, not so much. Now, this made no sense to our developers until they started looking. This is a log scale. They started looking at the effects of these routines here, which were our shared memory allocation and a shared memory barrier and deallocation routines. Now, on a runtime breakdown chart, these guys are not even visible because they're at such a small scale. But what we saw was that the effects in these routines were affecting transpose. And this becomes immediately visible in this chart. All right, so this is all profile data. Sometimes you need to know when do events occur. Is there a late sender, early receiver, that sort of thing in my application? If you need to see when events occur, you generate a trace. Now, immediately, traces are going to generate a lot more data because there's the size of the trace is proportional to the runtime of your code. So you're looking at gigabytes or terabytes of data. But it's very effective in showing messages sent between nodes, who is spending time waiting for messages, and so forth. Tau comes with the JumpShot trace visualizer tool, and it can also interface with Vampire, which is a commercial tool that's very good for trace visualization. If you want to generate the previous plot, you would use tau trace equals 1, and then call JumpShot on the trace data. And I want to emphasize that you can generate traces and profiles simultaneously. If you have a code that runs for 4 weeks, you don't want to run it twice to get this data. You can activate sampling, tracing, profiling, whatever, all simultaneously. Be careful of your overhead, of course. You pay for what you use in Tau, but if you need all these things at the same time, you can have them. And then finally, now Tau's a performance debugger in that sense, but it's really not a source code debugger. It can't track variables or place breakpoints or anything like that. But it can be useful in debugging your application. So one thing, so imagine you have a code that runs for 20 days and then finally dies, and you have no idea why. Well, if you had instrumented with Tau, you can send this Tau track signals environment variable. If there's a signal, such as a floating point exception or segmentation fault, bus error, so forth, Tau will cause all the nodes of your application to write out the performance data they've gathered up to that point, including a backtrace, showing across all levels of the call stack, where was that thread at the time of failure? So if there's a memory leak in your code that takes a very long time to manifest, and you eventually run out of memory, you can see it exactly in here. You'll see your memory usage slowly climbing until you finally run out of memory. Everybody dumps their call path, and it becomes, oh, well, that's obviously my problem. Now, this is especially nice because it works across multiple languages. What I'm showing here, I'll just go ahead, maybe this is a little more readable. this is an application that had a high-level Python wrapper calling Swig-generated C++, calling a Fortran solver. Now, and in fact, the memory allocated, the memory the Fortran solver uses is allocated in a different C++ component. So if you have a memory error in your Fortran component with memory allocated in a C++ component called from Python, you want to open this in your standard debuggers, good luck. With Tau, because we already have instrumented all the languages and all the call stacks, we can show you this across all language barriers. And in fact, if you right-click on one of the backtrace entries in Perf Explorer, it will open a source code browser and it will show you exactly what happened. Obviously, this math is not very good, and that causes the crash. So that's a high-level view of Tau. Tau is a very complex and I would say a rich tool system. So there's way more to Tau than I can possibly cover in 20 minutes, and I'd be glad to answer more specific questions and to help you learn more about specific features you might think would be interesting to you. So the thing I'm working on right now is called Tau Commander. Tau Commander is an approach to making Tau a little more user-friendly and a little more systematic. We have this system developed over 20 years involving many, many different powerful features, and users coming who come to Tau without a computer science background sometimes find themselves a little lost, like, where do I start? I don't know. Do I need to instrument before I measure, or what's going on? So I'm working on a project. It's a DOE SBIR Phase 2. We just finished our SBIR Phase 1. The goal is to simplify Tau usage. So we're developing a common framework for Tau that unifies all the tools into a single API, you might call it, which can then be the basis for new user interfaces to Tau. And this takes a lot of the guesswork and ad hoc development out of the user interface to Tau. It provides, and it gives us the ability to develop an intuitive, high productivity, top-level user interface that understands, what does the user want? And so we've already have some phase 1 results. This is from last year, and early results with our prototype are actually very encouraging. In one of our studies, we were able to reduce the number of steps across across 6 computing systems by about half using Tau Commander. And I'll talk more about how that was possible in a minute. And it also reduces the number of commands a user must know from an average of 8 to exactly 1. Now remember, Tau is a toolbox. So as you are performing different steps of your performance analysis, you're changing tools the whole time. And that means different compiler or different command line options, different configuration files. Usually the defaults are fine, but if you ever get lost, you're lost. I have nowhere to go. If you have exactly 1 command to deal with, it makes you much more productive. So the basic idea behind Tau Commander was, tell me what you want, not how you're going to get it. This is like the time, if you ever ask your friend, where do you live? They don't say, well, walk out of your front door and turn left and then go 3 steps to your car and drive down the store. And then, you don't want to have the blow-by-blow of how to get to your friend's house. It's 2014. Give me your address. I'll put it in my GPS, and I'll be there. So just tell me where to go. So the same is true here with Tau Commander. The idea is we have a Tau project. The Tau project gives context to the user's actions. Basically, as a scientist, all I know is I have chemical code. I want information about MPI, OpenMP, and I want to use sampling and direct measurement to get it. And that should be all you need to know. You would then create a Tau project that says, these are the things I want. Tau now goes, oh, OK, these are the things you want. I know how to do that. I can create the necessary Tau configurations. I can download the necessary packages. I can compile your code using the necessary flags because I understand what your goal is. And it also gives us a baseline for error checking. If you say in your project, I'm interested in time spent in or bottlenecks in MPI, then Tau can perform the necessary statistical analysis after the fact to look for those bottlenecks, so that when you open the analysis tool, it'll pop up and say, hey, look, you have MPI barrier and MPI send are major players in your code. You should go look at those first. And so it gets you right on track to finding what's the problem in your code. So this is the fully expanded Tau workflow. If you were a brand new user, this is the sort of thing you'd be faced with. It's not actually that bad. Most users just start right here and go straight to the bottom. The trouble is when you don't go straight to the bottom. When you get to about here and then get kicked back to the beginning because of some configuration error or missing compiler flag or something like that. That's a huge frustration. So our goal in developing Tau Commander was to simplify this tree by removing the troubleshooting segment and trying to minimize the number of loops back up to the top of the workflow. If you've ever used Tau in a really tricky code, you know exactly what I'm talking about. You get so close, and then at the very end of, you find that there was a missing Tau flag somewhere, and you have to start over. And that happens very rarely. I'd say that only happens, it's a few users, but it can happen. So we're trying to avoid that and make it very easy for people without a computer science background to get through this workflow quickly and productively. So our phase 1 result was to develop this workflow. This actually works, has been tested, where basically all your setup is to add Tau to your path. After you've added Tau to your path, you can create projects which say what you want. Then you apply Tau to your code, you get data, you look at the data, you have your results. And this worked. We tested this on about 120 systems, 126, and it was mostly productive, mostly effective. The new Tau interface right now is just a command line. Just shows you export path equals whatever to Tau, and then you have these subcommands. It's very sort of Git-like that you can communicate with Tau a string of subcommands to say exactly what you want. And if you leave one of these subcommands out, Tau has shortcuts. It can understand, oh, hey, you said Tau GCC something. GCC is a compiler. You probably meant Tau compile with GCC something. And then it'll go do that. So this was an example of the type of usage you can get from Tau, the kind of workflow. It comes down to 5 steps. It goes from Tau is not in your path to I have profiles in 5 steps. So it's highly productive. And the first thing I want to point out is that there's exactly one command you need to know from Tau, and that you put it at the front of your execution string all the time. So that's a huge advantage, that you know exactly what to call, and you always know where to call it. Now, I do want to remind you that what I'm talking about here, this Tau Commander product, this is still in beta. We're about 3 months into a 2-month project, or sorry, excuse me, 3 months into a 2-year project. And so the usage you see here is likely to change. Don't write this in your notes, right? This is not the way to get profiles right now. If you want to get profiles right now, go look at the earlier slides that say brief introduction to Tau, because that's the stuff that actually works and is sure to work. If you want to work with me to test this stuff, I'm glad to help you. But if you're interested in data today, now, go use Tau as described earlier. All right, so I'm going to finish with showing a few case studies. These were success stories with Tau done here at Argonne, where Tau was applied to an application with really great results. The first one here is IRMHD, which was done on Intrepid and MIRA by this team. We have John Perez, Benjamin Chadran, Tim Williams, and of course Samir from University of Oregon. They were working on IRMHD because it's a very interesting and sort of groundbreaking astrophysics code, and we want this to run as quickly as possible on the machines. Again, performance, efficiency, productivity. This particular story, you might already be familiar with it because it made the cover of HPC Source. It was such a great improvement in the application performance, and it's also on your ALCF newsfeed. So what they did is they performed a source-based, again, direct, not sampling, source-based instrumentation of IRMHD. They instrumented MPI, and they took measurements of MPI calls and volume. And they saw right away in the 3D view that IRMHD had significant synchronous communication bottlenecks. So what we have here is there's this MPI send, which is sort of sloping down here, and then an inverse pattern between MPI send and MPI barrier across, I think this is 2K cores right here. So this type of pattern jumps out at you immediately. They say, well, that's something we need to look at. They go and look at the data, and they say that, yes, MPI send and MPI bcast are causing the whole code to run much slower than it actually should. Furthermore, the time spent in FFT was also very large. So they were like, well, maybe we can improve that as well. So on Intrepid, the Blue Gene P, first step was, OK, so they have 3 profiles here. The blue profile is your baseline. This is the original unmodified IRMHD. This is the second profile where we have only optimized communication. They've replaced MPI send and MPI barrier with various MPI iSend and so forth calls to overlap communication and computation. Just changing the communication substrate, they was able to improve performance by, or reduce time spent in these routines by about half. So a huge immediate performance benefit. Now these codes are running for days. I think these profiles, so for example, there are 448 hours were spent on this advanced one snap routine. So these are very long runs we're talking about. Cutting that in half is a huge benefit. An immediate, I mean, just the power bill alone is fantastic. The second thing they did was implement a more efficient underlying FFT, or sorry, give a more efficient implementation of the underlying FFT, which is the green bar here. And again, we see a huge improvement in time spent in these routines. The net effect was that the code end-to-end was 7 times faster once they were done optimizing it based on the data that Tau provided. So that was on Intrepid. Let's go to MIRA. I'm sorry this is so weak here, but okay, so on MIRA, if you put the data on a topology view, you can see that there's a hotspot in this corner of the topology. There's a cluster of bright red nodes here. And then if you look at the 3D view, there's this nasty spike right here in MPI all-to-all. It turns out this was caused by a load imbalance. So rebalancing the load and reevaluating how the cores are loaded in the first place can have a significant performance improvement on MIRA, which is this is what they did. They went and they removed unnecessary MPI barrier calls. This reduced time by about 6 to 12% across most of the calls. You can see here MPI barrier, blue is the baseline, and it's just gone. There's no MPI barrier left in this part of the application. And then by redistributing the load, they were able to get an overall runtime improvement of about a reduction of 30%. The optimized code was 70% the runtime of the original code. So another example was in NWChem. This is work done in 2012, but it's still very relevant even on MIRA. This is a fun example because NWChem, first of all, it's an important code, and it also uses this ARMC communication library. So this is an example of Tau operating in a strange environment with a communication substrate that's not necessarily MPI or OpenMP or so forth. This is a one-sided communication substrate that provides a unified view of physically distributed arrays. And the guys running the study wanted to know what is the performance of representative workloads on various platforms, and how can we optimize that? It was published here in CCPA, right? And oh yes, so they wanted to understand data server compute node interplay. Basically, how do we best distribute this data? And then finally, what are some of the trade-offs if we allocate a separate core for just handling communication and interrupts? Again, they did a source-based instrumentation direct. They also used Tau's abilities to wrap libraries to generate a ARMC interposition library called Tau PRMC. They wrapped the external libraries, such as BLAS, and they ran this on Fusion and Intrepid. Now, I spoke with these guys. They say that MIRA and Hopper are going to go to the same scale, but they're going to show the same performance. So I think these numbers are still relevant. The first thing that's immediately obvious when they opened this, so they ran from 192 cores to about 1K cores, and they saw no scalability at all. The difference here, so as the number of cores increased, the time in this blue routine just skyrockets. And what we're seeing, this is the time ARMC spends copying buffers from memory. Now, in the second run here, you might not be able to see the scales. This goes to 10,000. This goes to 1,600. So we're 7-8 times faster in this run. And all they did was pin the buffers ARMC uses for communication so that it's not chasing memory all over the place. So first, notice there's no scalability here. This is scaling, and overall runtime is significantly improved. This is a very dramatic effect, and it was immediately obvious when you open the profiles in PerfExplore. The next test is to allocate a separate core specifically for communication and interrupt handling, this CHT thread. Doing this shows a moderate performance improvement on BlueGeneP. And again, this is visible in the Perf Explorer charts, stack bar chart here. We see that scalability is improved. So I want to conclude with reminding you that Tau is free, open source, BSD license. You could go download it, play with it. It's already available on the ALCF systems. It works on your MacBook or your PC laptop or your Android phone even. We have a Linux distribution. This is HPC Linux is a distribution of Linux done by ParaTools, and it includes Tau, Vampire, Intel compilers, a great many fun toys and goodies that are already pre-installed and configured and set up with examples so that you can learn how to use them effectively without any startup time. So if you download the live DVD image here and open it in something like VirtualBox, you can get up and running really quickly on your home system or laptop. I want to thank all the sponsors who have contributed to Tau, all the developers over the past 20 years, and especially the Department of Energy and Argonne for having me here. And I'll be glad to take your questions. So thank you very much. Yes?
How do you evaluate Tau's ability to interact with more complex build systems if you have an application that, because of the inevitable complexity that does exist, can't have a flat makefile?
Of course.
How well does Tau cope with, say, Argonne for CMake-based config systems?
Of course. So Tau works very well within these systems. I've used it with CMake. I've used it with several homebrew build systems. The beauty of it is all you have to do is get the Tau compiler wrapper scripts in there instead of the name of your compiler. So if you're calling CMake, set your CMake C compiler, -D CMake C compiler, CMake CXX compiler, Fortran compiler, and so forth. If you have your own custom build system, just change your configuration files. So instead of calling GCC or XLF, call taocc.sh or taof90.sh. And yeah, so it was pretty straightforward, actually.
Any other questions?
Yes?
Yeah, I mean, in the past, I feel like I've had trouble with those wrappers in Tau because, like, the arguments that you pass to certain compilers are always different. You're using PGI or GCC, things like that. But this is many years ago. Have you guys smoothed that over?
Yeah, so that's the purpose of the Tau makefile. If you select the correct Tau makefile, so you will see different Tau makefiles for each compiler. There will be a -PGI or a -Intel or -GCC or -GNU flag actually in the name of the makefile. So if you're working, you just match the makefile to the compiler, and then the Tau makefile will make sure that the correct options are passed. I think on MIRA, I think there's GCC and XLF configurations already.
Okay, does anybody else, we have time for one final question?
Yes?
So in your visualizations, you had heights of bars and they were also colored, right? Do those two things mean the same thing?
Oh, the 3D visualization.
Right.
They can mean different things. It's configurable. So in the example, let's just pick an example. In this particular chart, they are the same. That's because here we have height metric, and I can choose exclusive or inclusive or PAPI or whatever time I need, or whatever metric I need. And then this is color metric, which you can do the same with.
Okay. So they can be something different.
Yes.